Today I want to look at some nice applications of the Sylow theorems, which we covered in a previous video. So let's recall what those are first. So let's say that p is a prime number and we have a group of order m times p to the r where p does not divide m. So it's like we've factored out all of the possible p's from the order of the group. Then the subgroup, which we'll call capital P of G, is called a Sylow P subgroup if the order of capital P is P to the R. So it achieves that largest power of the prime. And then, well, there are three Sylow theorems, and here they are. So let's suppose that we've got a group of that order where, again, the prime doesn't divide M. I don't have that, but we can bring that from the definition. Then the first Sylow theorem says that G has a Sylow P subgroup. So it will have a subgroup of order P to the R. The second Sylow theorem says that all Sylow P subgroups are conjugate. So what does that mean? So in other words, if we have two of them, H and K, then there exists a G and G such that K is GH inverse. It's the conjugate of H with little g. Now let's observe that if there is a single Sylow P subgroup, then it is necessarily normal. And we can see that because this conjugation action brings us into another Sylow P subgroup. But again, like I said, if it brings us into another Sylow P subgroup, but there's only one Sylow P subgroup, then it brings it back into itself. But that's exactly the condition for normality. And then finally, if NP is the number of Sylow P subgroups, then NP is congruent to 1 mod P, and NP divides M. So this allows us to do like some nice arithmetic to determine whether or not groups are simple or whether or not it's possible for groups to be simple. And that's what we're going to do here. So we're going to start with the following proposition. And this takes care of groups of lots of different orders. So let's say that P and Q are primes where P is less than Q and G is order P times Q. Then G has a normal subgroup of order Q. But if it has a normal subgroup, then it is not simple. And then furthermore, if Q is not congruent to 1 mod P, then G is cyclic. So that even breaks it down more. We can classify lots of different groups as cyclic groups in this case. Okay, so let's get going. So let's let Q, capital Q, be a subgroup of G, and it's not any subgroup. It is a Sylow Q subgroup. So it's one of those subgroups of order Q, which we're guaranteed to have by the first Sylow theorem. And then let's set n sub q equal to the number of Sylow Q subgroups, just like we have over here in our theorem. So what do we know? Well, we know that n sub q is congruent to 1 mod q. And we also know that n sub q has to divide p, because that's what's left over. But let's observe the following. This n sub q is 1 mod q. That tells us that n sub q must come from the set 1, 1 plus q, 1 plus 2q, and so on and so forth. But then the fact that n sub q divides p and p is prime, that tells us that n sub q can only come from the set 1 and p. But then what do we know? We know p is less than q. So since p is less than q, all of these are too big. And we know that all of these numbers are too big because all of these numbers are bigger than this number p here. But that only leaves us one possibility for n sub q, and that is this number 1. So here we have n sub q must be equal to 1. But then by that result that I just verbally said, which is a nice homework exercise, we get that q is normal in G. So in other words, we have it. Okay, cool. So that proves this first part, that G has a normal subgroup of order Q. We just proved that. Now we want to show that if Q is incongruent to 1 mod P, then G is cyclic. So let's maybe dot these just to say that we're moving down to the second setup here. So now we'll suppose that Q is incongruent to 1 mod P. And let's also say that P, capital P, a subgroup of G, is a Sylow P subgroup. Cool. And let's use N sub P for the number of Sylow P subgroups, just as we did for N sub Q. I won't rewrite it though. And now let's notice that N sub P has to be congruent to 1 modulo P. And let's observe that N sub P must divide Q. But notice this tells us that N sub P equals 1 or it equals Q. But then since Q is incongruent to 1 mod P, but N sub P is congruent to 1 mod P, that tells us that this possibility of N sub P being equal to Q is actually impossible, which means that N sub P is in fact equal to 1. But then furthermore, that brings us to see that P is also a normal subgroup in G. So let's see, we've got G, our group, and then we've got normal subgroups of order little p and little q. So now let's see how we can use that to show that G is cyclic. Okay, so far we've shown that we've got a subgroup of order P and a subgroup of order Q that are both normal. And now I'd like to observe the following, and that is if we take the intersection of P and Q, we necessarily simply get the identity. Now why is that? Well, the intersection of P and Q is going to be a subgroup of P and it's a subgroup of Q. But since it's a subgroup of P, its order must divide P. But then since it's a subgroup of Q, its order must divide Q. But then you've got a number that has to divide a prime P and a prime Q. Unequal primes P and Q, but there's only a single number that does that, and that is the number 1. But then if the order of P intersect Q is 1, it's simply the identity element. Okay, then what do we get out of that? Well, let's observe that we have 2 normal subgroups. So that means that we have their internal product, P times Q, and that's going to be a subgroup of G. And then also we know that this internal product, PQ, has order little p times little q. And so that's because you can write the order of this product subgroup as, well, let's just recall really quick. So this is in fact equal to the order of P times the order of Q over the order of the intersection of P and Q. That's kind of a standard result. But that intersection is just the identity element, so that's 1, so that means that, well, we get that result pretty quickly. But now notice that means that we've got a subgroup of G that has the same number of elements as G, but that means that G is in fact equal to this product of subgroups. And next we'll show that these are abelian. So let's now notice that P must be cyclic, and we'll say that it's generated by X. How do we know P is cyclic? Because it's a group of order prime. And then similarly, Q is cyclic for the same reason, because its order is prime. Okay, so now let's look at the following object. So let's look at X inverse Y inverse, and then X, Y. So let's notice that if we look at it in this form, X inverse Y inverse X, then this is going to be inside of Q. That's because Q is normal. And so whenever anything's normal, if you conjugate it by anything from the group, you land back in the group. But then let's observe that we're then multiplying that by something in Q. So if we're multiplying something in Q with something in Q, then you land back in Q. Now let's compare that to this thing right here, y inverse xy, which is necessarily in P. And that's because P is normal. But then this x inverse is also in P, meaning the entire term is in P. But let's observe that means the entire term is inside of P intersect Q, which we already claimed was the identity. But now we can left multiply by x, and then left multiply again by y, and we'll end up with y times x equals x times y. But now let's observe that means that G is abelian. Well, and why is G abelian? Because since P is generated by x and Q is generated by y, that means that G is generated by x times y. But then x and y commute, so that makes the whole group abelian. But now that means the following. So G is equal to P times Q, like we said. But then that's going to be isomorphic to P times Q, or cross Q, I should say. And that occurs if everything from P commutes with everything from Q. That's a previous result. But then that's going to be isomorphic to ZP cross ZQ, because every cyclic group of order P is isomorphic to ZP, and similarly for cyclic groups of order Q. But then since P and Q are necessarily relatively prime, this is isomorphic to ZPQ, which itself is cyclic. So we've shown that G is isomorphic to a cyclic group, which is what we wanted to do. Okay, so now let's look at a quick application of this, and we can in fact fit this application right here. And that is every group of order 15 is cyclic. Well, why is that? Well, let's notice that 15 is equal to 3 times 5. So it's the product of two primes like our setup here. And then the larger prime is incongruent to 1 mod the smaller prime. In other words, so that means if a group is order 15, it satisfies all the conditions right here, which means it is cyclic. Okay, so now let's move on. Okay, so now let's look at groups of order 99. In other words, 9 times 11. So this is different than the last case because this is not the product of two primes. We have 3 squared times 9. Okay, so that means we've got Sylow 3 subgroups and we have Sylow 11 subgroups. So let's look at each of those separately. So let's say Sylow 3 goes here, and let's say that Sylow 11 subgroups are going to be talked about here. So for Sylow 3 subgroups, we know that in 3, the number of Sylow 3 subgroups has to be congruent to 1 mod 3. And we also know that in 3 must divide 11, because that's what's left over here. So that tells us that in 3 must come from the set 1, 4, 7, 10. Let's see, the next one would be 13, so on and so forth. Those are all the numbers congruent to 1 mod 3, intersected with 1 and 11. But then there's only one number intersecting those two sets, and that is the number 1. So, well, what does that tell us? Well, immediately we know that if n is equal to the Sylow 3 subgroup, then we know that n must be normal in G. Using the same sort of argument that we used previously, that if you have a unique Sylow P subgroup, then it has to be normal. Okay, so now let's look at our Sylow 11 subgroup. So notice that N11 is going to be congruent to 1 modulo 11, and then we know that N11 has to divide 9. But now very, very quickly we'll see that N11 is also, let's see, N11 is also equal to 1, and that's because the N11 must come from the set 1, 12, let's see, the next one is 23, 34, so on and so forth. That's the condition that it's 1 mod 11. But then it also has to come from the set 1, 3, or 9 because it has to divide 9. But there's only a single number from those two sets, and that is 1. So now what does that tell us? Well, that tells us that if we set M equal to the Sylow 11 subgroup, then we know that M is also normal in G. But now let's see what we can do here. So now we can use a really similar strategy to what we did before. So now let's note the following, and that is that M intersected with N is going to be the identity, and also that Mn is going to be a subgroup of G if the order of Mn equal to, well, the order of M times the order of N over the intersection. But in this case, that's simply equal to 99. N is a Sylow 3 subgroup, but remember that means it is order p squared in this case, or 3 squared in this case. So that tells us that what? G is in fact equal to M times N. And now we can do the same kind of thing to show that everything from M commutes with everything from N. So let's do that. So let's take maybe little m from capital M and little n from capital N, and then note that M inverse N inverse Mn must be from the intersection of M and N, using exactly the same strategy that we did before. So this bit right here must be in M because M is normal, and then it's being multiplied by another thing from M. So the whole thing is in M. And then this thing right here must be inside of N because N is normal. And then it's multiplied by something in N, so it must be in N. So it's got to be in both of those, but it being in both of those means that it is equal to the identity. But then pretty quickly you get Mn equals Nm. Okay, cool. But then if G is the product of these two subgroups and everything in one of them commutes with everything in the other one, that tells us that G is in fact isomorphic to. But then check it out. We've got M is a Sylow 11 subgroup. So that means that M is only possibly Z11. Now, since N is a Sylow 3 subgroup, it has order 9, there are two possibilities for N. Those are the possibilities for our group G. And just so we're clear here, the M is always this Z11, and the N will either be Z9 or Z3 cross Z3. Okay, nice. Now let's do another example. Is normal by the result that we've been using over and over and over again. So let's instead look at case 2 if N7 equals 8. And now we're going to play the same sort of game that we did before, counting elements. So again, let's say that these blue bubbles are all of the Sylow 7 subgroups. So we've got one like that, maybe we've got one like that, maybe we've got one like that, so on and so forth. So intersection of all of them is simply the identity, and that's because each of these groups are of prime order. And then outside of their intersection, we have what? Well, we have 6 more elements. So I'll just put 6 more here, 6 more here, and 6 more here. And then obviously this goes around. This is for a total number of 8 Sylow 7 subgroups. And so now putting this all together, that means there are 6 times 8, because we've got 6 elements and we've got 8 subgroups. In other words, we've got 48 elements of order 7. Okay, nice. But what does that leave? So that leaves the total number of elements in the group, 56 minus 48, but 56 minus 48 is 8. And these are elements of orders, well, what? All the other possible orders. But the order of an element must divide the order of a group. And so in the end, these are going to be elements of orders 1, 2, 4, or 8. Okay, cool. I guess this doesn't preclude the possibility of there being an element of order 56, but if there's an element of order 56, then we're like kind of immediately done because we have a cyclic group. Okay, so anyway, we've got 8 elements of order 1, 2, 4, or 8. So that means that these must form the single Sylow 2 subgroup. Because if we had more than one Sylow 2 subgroup, well, we wouldn't get the maximum number of elements like we do here, but we would get more than 8 total elements. But, well, what does that mean? So that means that N2 is equal to 1, but then that means that the single Sylow 2 subgroup must be normal, but if it's normal, then our group is not simple. Okay, so let's see one more technique for showing groups aren't simple, and then I'll leave you with some exercises. Next up, let's show that groups of order 6,545 are not simple. And well, the factorization here is 5 times 7 times 11 times 17. Okay, so let's look at the number of each type of Sylow subgroup. Notice that we've got Sylow 5, 7, 11, and 17 to look at. So we'll use our standard notation. So N5 is the number of Sylow 5 subgroups. And notice that N5 is congruent to 1 mod 5. And N5 has to divide the rest of the terms in the group. Or I guess I should say the product of the rest of the parts of the order of the group. So in other words, it has to divide 7 times 11 times 17. So now putting that all together, that leaves us with the following 2 possibilities for N5, and that's 1 and 11. So now moving on to N7, we know that N7 must be congruent to 1 mod 7, and N7 has to divide 5 times 11 times 17. But now putting all that together, that leaves us with, again, only 2 possibilities of N7, and in this case, it's 1 and 85. And then let's see, what's next? So N11 will be next, so that's going to be congruent to 1 mod 11, and N11 will divide 5 times 7 times 17. So those restrictions mean that N11 has, well, again, 2 possibilities. And in this case, they are 1 and 595. Okay, so one more. So N17, which is of course congruent to 1 mod 17, and then N17 has to divide 5 times 7 times 11. So putting that all together, N17 is either 1 or 35. Good. And so now, let's observe that if this group, I didn't name the group above, but let's name the group G, is simple, that means that none of these n's are equal to 1. Because let's recall that if we've got a unique Sylow subgroup of a certain order, that's necessarily normal. So if it's simple, then we won't have a unique one of any of these orders. Okay. So if G is simple, then that means that N5 is equal to 11, N7 is 85, N11 is going to be 595, and then finally N17 will be 35. And now I want to show you guys this counting argument, and we're going to do most of the work, or I should say the explanation, via the Sylow 5 subgroups. But then we'll use this strategy with all of the other subgroups as well. So here, let's say that our Sylow 5 subgroups are drawn maybe with these little bubbles here. So let's say this is one of our Sylow 5 subgroups. So it has the identity right here. But then other than the identity, we have 1, 2, 3, 4 elements of order 5. But these 4 elements of order 5 clearly generate the entire Sylow 5 subgroup because it's necessarily cyclic. Now let's draw another Sylow 5 subgroup. So that's going to look something like this. And so it will intersect only in the identity. We know that it intersects only in the identity because if it contains one of these other things, which is a generator of this whole subgroup, then it will be exactly this subgroup. So that gives us 4 more elements right here of order 5. And now I think you could probably see where we're going. We've got another Sylow 5 subgroup that's going off this way. It intersects in the identity, leaving us with 4 elements of order 5 here. And then, well, that kind of thing goes all the way around for all 11 Sylow 5 subgroups. So putting this all together, that means that there are 11 times 4, in other words, 44 elements of order 5. Good. So we just counted up all of the elements of order 5. But now we can do the same kind of game with all of these other things. So let's notice that there will be 6 times 85, but 6 times 85 is in fact equal to 510. And these are going to be elements of order 7. And that's because the Sylow 7 groups will not intersect in anything except for the identity. And there are 85 of them, and each of them have 6 elements of order 7. And now, well, we continue. There are going to be 10 times 595, but that's of course equal to 5,950 elements of order 11. And then finally, to finish off this counting argument, there's going to be what? There will be 16 times 35, but 16 times 35 is equal to 560 elements of order, let's see, we're here at elements of order 17. So far, how many elements have we accounted for? Well, let's check it out. So we have at least the following number of elements. So we've got an identity element, so that just is a single element. That's an element of order 1. And then we've got 44 elements of order 5 from right here. Let's see, we have 510 elements of order 7. We have 5,950 elements of order 11. Then we have 560 elements of order 17. But now adding all of that up, you'll get the number 7,064. But that's extremely problematic because notice our group only has 6,545 elements. So we've just accounted for more elements than are in our group. So what does that mean? Well, that means it's impossible for there to be 11, 85, 595, and 35 Sylow whatever subgroups. But the only other possibility is for one of those to be equal to 1. That means this is 1, this N7 is 1, N11 is 1, or N17 is 1. Now, whichever of those is 1, since it's the unique Sylow subgroup of its given order, that means it is a normal subgroup. But if it's a normal subgroup, well, that means our group is not simple. Okay, let's look at another one of these. Okay, so now we're going to show that groups of order 48 are not simple. And the technique that we're going to use here, I like a lot. So let's start by observing that 48 is 16, in other words, 2 to the 4 times 3. So that tells us we're going to have Sylow 2 and Sylow 3 subgroups. And let's observe that the number of Sylow 2 subgroups must be odd. In other words, it is congruent to 1 mod 2. And the number of Sylow 2 subgroups must divide 3. But now putting that together, notice that means that N2 is either 1 or 3. So that's a pretty simple calculation. Now let's move on to the next case. So we know that N3's got to be congruent to 1 mod 3, and N3 must divide 16. So that means that N3 has to come from the set 1, 4, or 16. Those are the numbers, those are the powers of 2 between 1 and 16 that are congruent to 1 mod 3. Okay, so now let's break this down into maybe a silly case and then the case that will require all of the work. So let's say our first case is what happens if N2 is equal to 1. But of course, if N2 is equal to 1 by this argument that we've been using over and over and over again, that means that the Sylow 2 subgroup is normal. but then we've got a non-trivial normal subgroup of our group, which means our group is not simple. So the second case will be what happens if n2 is equal to 3. So let's suppose that n2 is equal to 3, and then let's let h1, h2, and h3 be the 3 Sylow 2 subgroups. Okay, now what are we going to do with those subgroups? Well, let's notice this. For all little g in the group G, we again didn't name the group, but let's call the group G. We know that G hi G inverse is going to be one of these right here. And that's by our second Sylow theorem here that says that, in this case, all the Sylow 2 subgroups are conjugate. And so that means that this will conjugate hi into another one of these things. Furthermore, it's not going to conjugate it to itself all of the time, because otherwise hi would be normal. So the way that we can write this kind of in general is that this is going to be equal to h sub sigma g evaluated at I, where sigma g is an element of S3. Because this group, via conjugation, is just permuting these Sylow 2 subgroups. Now, let's notice that that gives us a map, which we'll call phi, and that map goes from G to S3. And the map is simply defined by phi of G is equal to sigma G, where again, sigma G is defined by how this element G conjugates and permutes the Sylow 2 subgroups. Okay, cool. So now let's first notice that this map phi is non-trivial. In other words, the image of phi is not simply equal to the identity element in S3. Recall that we would write the identity element in S3 like that. And why is that? Well, that's because none of these hi's are normal in the group. And, well, how do we know that none of them are normal in the group? Well, it's simply because there are 3 Sylow 2 subgroups, and a Sylow P subgroup is normal if and only if it's the only one. And that, again, is something that follows from the second Sylow theorem. Okay, so it's not normal. But then it not being normal means that, well, there is a group element that will not fix this. But the group element that will not fix this will correspond to something other than the identity in S3. Okay, so anyway, we've got the image of phi is non-trivial. Okay, now let's check that it is a homomorphism. Okay, so how can we do that? Well, we can do that with the following little calculations. So let's look at x sub, let's see, sigma sub g1, g2 evaluated at I. And so, well, what is that? Well, that's going to be the following action. So we've got g1, g2 conjugating hi. So that means on one side we've got g1, g2, and then on the other side we have g1, g2 inverse. But now let's rewrite that as g1, and then here we have g2 hi, g2 inverse, and then g1 inverse, just by the so-called shoes and socks theorem. But now let's observe that that is equal to g1 h sub, let's see, sigma of g2 evaluated at I, and then g1 inverse. And that's just by the fact that g2 will conjugate via that permutation. But then finally, that's going to be equal to h sub sigma 1 composed with sigma 2 evaluated at I. Again, that's because that's how g1 permutes the Sylow 2 subgroups. But now let's observe, just by extracting the subscript here, that means that sigma g1 g2 is equal to sigma g1 composed with sigma g2. But notice that sigma g1 g2 is simply phi of g1 g2. And then over here on the right, that's phi of g1 times phi of g2. But that's the condition of this thing being a homomorphism. Okay, so now we've got a homomorphism that is non-trivial from G to S3. Let's see what we can do with that. So we just argued how we created a non-trivial homomorphism from G to S3. Now let's notice a couple of things. So non-trivial means that the image of phi is more than just the identity. But the image of phi being more than the identity tells us that the kernel of phi is going to be less than the entire group. So this is not equal to the entire group. But then now let's just look at the following. Notice that the number of elements in S3 is equal to 6. That's 3 factorial. Then 6 is less than 48, which is the number of elements in the group G. But what does that mean? Well, if we've got a bigger group mapping into a smaller group, that means that our function cannot be injective. In other words, the kernel here is not equal to simply the identity. Because if it were equal to the identity, we would have an injective homomorphism, but that can only occur when we're mapping from something smaller or the same size to something larger or the same size, I guess I should say. But check it out. What do we have? We've got something, a kernel, which is not the whole group, and it's not just the trivial subgroup. And we know that the kernel is always a normal subgroup. So we've got a normal subgroup of our group that's not the whole group and it's not the trivial group. In other words, we've got a non-trivial normal subgroup, meaning our group cannot be simple. Okay, so now I'm going to leave you with some exercises. So to practice the techniques from this video, let's try to show that there are no simple groups of the following orders.